Welcome to the 8th lecture of combinatorics. In the last class, we stopped with an example of a bijective proof. We were considering the number of northeastern lattice paths from 0 0 to n n that never go above the diagonal x equal to y, the main diagonal. And the other thing we were considering was the number of ways to fill a 2 by n grid with the elements of 1, 2 up to 2n, 1, 2, 3 up to 2n using each element once, exactly once, so that each row and column is increasing. Row is also increasing, column is also increasing. So this is this such kind of rectangles are 2 by n rectangles are is called the this kind of rectangles are called the standard Young tableau. We are saying that this 2 by n Young tableaus, so the number of such tableaus are equal to the number of northeastern paths, right, in the diagonal. So let us do the proof once again. So we just want to set up a bijection between these two things. One side we have the number of northeastern lattice paths. So something like this. This is 0 0, right, something like this, right. So let us say this is n, and here so this is n. So this is the main diagonal. So maybe we can use a different pen, right. So this is the main diagonal. So let us say this is n by n, this is the n by n point, this one, right. So now what we are interested in is, so you remember what is northeastern path. So we are driving from here to here, these are the roads. We can either go straight, maybe we can go like this, or we can go like this. So we can go like this, and so either we can go upward, I mean north direction, or in the east direction, means straight, right, towards right. So this is how many such paths are there to reach here is the question, right. But now the extra condition is that we should never cross above the main diagonal. I mean we can touch these points, but we should never go beyond this. Maybe we should not go here like this, right. We are not allowed to take this kind of things. So now we are actually not counting these paths here. We will do it later using Catalan numbers, but that will come later, right. As of now our intention is just to set up a bijection, show a bijection between these kind of objects. Objects are see, one of the objects is a path starting, say something like this, say this will be one such object, right, which we are interested in. Several such objects, as you can see. Set up a bijection between these objects and the standard Young tableau of the 2 by n type. So this 2 by n means this is 2 columns are there, sorry, 2 rows are there, and then n columns are there, 1 2 3 up to n, and this is 1 2, right. So there are actually how many squares here? 2n squares are there, right. So we have to fill these squares from this set 2n, right. That means 2n means 1 2 3 4 up to 2n, right. Now of course, which means that every number here has to be taken exactly once and put somewhere, right, because every one of these 2n things should go there. We should not repeat, right. And but the only constraint is that when you read after filling in, when you read from this direction, that means in a row when you go from left to right, it should increase. Similarly in the second row also. Similarly in every column, from you come from top to bottom, it should increase. There are only 2 elements here. It should be, this should be smaller than this, that is what it says, right. So we are claiming that this number is exactly equal, number of ways you can fill it using this 2n in such a way that our constraint is satisfied is exactly equal to the number of ways we can drive from 0 0 to n without ever crossing the main diagonal, always keeping below the main diagonal, right. So, how do we show this thing? So, that we just need to show a bijection. So, we will show first we will show that suppose you have a route here, driving route here. Now, how to construct a Young tableau for that? We will say that there is for that, for each of them I can construct a unique tableau, so that it is a function, right. So, this is for instance what I do is, so I will show filling in this, right. So, it is like, see for instance here first step is east step, right. So, therefore, whenever I take eastern step, that means rightward, that step number, this is the first step, this is the second step, this is the third step, the fourth step, how many steps will be there total? 2n steps will be there, right. The step numbers, if it was an eastward step, then we will fill it in the upper row, otherwise we will fill it in the lower row, and we will fill it in the order in which it comes. For instance, here the first step, right, that will go, we write here 1, the first step is in the east, I mean east, and then here this is upward, I mean northward step, that is second step, then because it is a northward step it will come here, and then here the third step is eastward, so that will come again here, and what about the fourth step? Fourth step is again northward, that will come here because it is northward, and what about the fifth step? Fifth step, fifth step, sixth step, seventh step, fifth, sixth, seventh, all of them are eastward. So, we will write it fifth, sixth, seventh, and then now eighth step, eighth, ninth and 10th are northward. So, we will write like this, like that we can keep on filling. So, see this in this case we reached n was equal to 10, n was equal to 5, therefore, we reached in 10 steps to the point n comma n. So, otherwise we keep filling like this. So, we claim that looking at that route we have filled the tableau. So, it is indeed satisfying the constraints. Of course, we have been filling the step numbers. So, we have taken numbers from 1 to 2n. So, because 2n squares are there, all the squares are filled because we consider 2n numbers, and then of course, we were considering the step numbers in the increasing order, therefore, and we are filling here from left to right, therefore, the rows definitely increase from left to right. The only thing we have to check is that the columns also increase from downward, down to bottom in this direction, right. Here 1 2 3 4 5 8 6 9, see it is increasing. So, why am I sure that it will always increase? Suppose it does not increase, right, at some point of time. For instance, it so happened that the first time, so for instance, I can locate the first column where it is not increasing, maybe this is the first column, here it is increasing, here it is increasing, here it is increasing, here it is not increasing. That means, here we have a number which is bigger than this number. So, we can stop at the point we filled it. That means, we have filled it, fill this, fill this. Maybe I do not know whether this is filled or not, but we have filled this, this and this, right. Upper row we do not know, because we have in the lower row we have reached up to here, right. Here upper row we are sure that this is not filled, right. Whether this is filled or not, we are not sure. But now, because I have filled the lower row at least this many times, this is the ith row, that means I times I have filled something, means I steps were taken in the northward direction, that is what. but on the other hand this square is not filled at all, right. That means the maximum number of steps taken by that time towards the east is strictly less than I minus 1 maximum. It can be even smaller, but I minus 1. But then you can see that if you have taken gone only I minus 1 steps, say 1, 2, 3, 4 steps eastward, but I steps, that means 4 plus 1 5, say one more step northward, that means you will be above the main diagonal, right. 1, 2, 3, 4, 5 you will be above, because if you are here, the maximum, if you want to keep below the main diagonal, it means that you can take maximum by the time 4 steps eastward. See, if you have gone I steps here, that means you can only take I steps northward also, but you have seen that we have already taken I steps northward, so only I minus 1 steps are taken eastward. So it means that you are above the main diagonal. That is why it will never happen, because you know that our path was always below the main diagonal, right. The path maintains the property that at any point the number of steps taken to the east is at least as much as the number of steps taken to the north, right. So therefore it is not possible that the ith, say ith column, right, gets filled in the below part, in this gets filled before this, that will never happen, because if this gets filled before this, then that means the number of steps taken in the north direction will be more than the number of steps taken in the east direction. That is why it will never happen, right. So we have indeed got a Young tableau for each of the valid Young tableau from each path, and it is very clear that each path will give rise to a different table, because you know for instance, if two tables are same, that means the specific steps taken to the east are same in both the tables, right. That means the paths are also same, right. So, but the paths were different, therefore the tables will also be different for different paths. So, what we have shown now is that for each path we have a table, and for two different paths we do not have the same table, right. That is what we have shown. So, therefore right, each path we have a unique table, and then so okay, if you consider two different tables, that means, but then one will wonder whether is it possible that there are some tables for which there was no paths, that also we have to verify, but that will definitely will not happen, because once you get a table you can look at the entries in the table. So you can imitate the path by this is I look at the step number, this is 1, so wherever is the 1, so I will put that step in the east direction. Second step, where is the second step? So if it is here, then see for instance here 1, so I will write it 2 I see, so that should be like this. 3, so that means in the east direction. Suppose 3 I see here, I would have gone upward, but of course you will not see it that way. Suppose 3 it is in the eastward, so then I look for 4, 4 is here. If 4 was here and 5 was here, then definitely I would have taken 3, 4, because in the east direction, and 5 is coming next like this, right. And then 6 I am seeing here, so I will go here. 7 I am seeing here, then 8 in the north, right, 9 in the north direction, 10 in the north direction, like that I can construct a path. Of course, because of the property that then whenever I am at a point, so for instance I have already taken more eastern steps than more or equal eastern steps than the northern steps, I will be always below the main diagonal. That is why there is a one-to-one correspondence between these two, right. So, okay, so our point was just to illustrate the bijective proofs. That means here for instance the number of paths starting from 0 0 and reaching n, which always keeps below the main diagonal. It at first look it looks very different from the other object we consider, namely a matrix 2 by n matrix, a tableau where we are filling in numbers in the squares, and we have put just two rules. That means along the rows the numbers should increase, and along the columns downward the numbers should increase, right. And this is very this is a very natural restriction. That means usually want the rows to increase, columns to increase. It's not very unusual thing. It's not a cooked up rule, right. So, but how many ways of filling are there, filling the table are there. So, at one look it may seem these two problems are very different, but then by setting up the bijection we have shown that both the problems are one and the same, the count will be same, right. So, this is this kind of arguments are very common in combinatorics, because in many cases one type of thing may be easier to count than the other type. That is why we set up the bijection and then we connect to the other. Maybe it is already known how to count one type of object, and then by setting up the bijection from the other object to this one. So, we already we can count the other type of objects also, right. Otherwise thinking directly about it may be a little more complicated. Of course, one has to keep this kind of ideas in mind. Now we will consider. So, we have learned okay, already we have learned the binomial coefficients, the so called n choose r. This choose means we are choosing, see from that subset interpretation of binomial coefficients only the word is coming. There are n element set, from that we are choosing an r element subset. So, that is why n choose r. How many ways we can choose r element subsets from n element set. Now, we will study certain properties of this binomial coefficients. The most important ones, the most famous ones we will consider. They are really elementary. Let n and k be non-negative integers, so that n less than equal to k. So, that we are only considering positive integers, n and k are positive integers here, and k is also 0. It k can also be this can also be 0 of course. So, we are assuming k is less than equal to n. Then we want to show that n choose k equal to n choose n minus k. This identity, this is called symmetry identity. Symmetry. Why is it called symmetry identity? Because n choose n minus k is equal to n choose k. Some symmetry is there about it. For instance, if you consider the combinatorial coefficients n choose 0, n choose 1 and n choose 2 and like that up to n choose n, right. So, we look at, so this is n is same here, okay, n is same here. Now, 0 and n. So, we read from this side or this side, this is kind of symmetrically positioned from both ends, right. If you look from the left and right, this n choose 0 corresponds to n choose n somehow, right. N choose 1 will correspond to n choose n minus 1, right, and similarly n choose 2 will correspond to n choose n minus 2, position wise at least, right, reading from here or reading from here, right. So, that way n choose k correspond to this n choose n minus k, because this is the k plus 1 from here, this will be the k plus 1, n minus n choose n minus k will be the k plus 1th from here, So, they are equal is what it says. So, maybe to get this picture a little clearer, we can introduce one pictorial way of writing, or maybe tabular way of writing these combinatorial coefficients, which is known as Pascal's triangle. So, it is like this. So, we first write n choose 0 in the first one, then we write n choose 0 and n sorry. So, not n choose 0. So, we can start with the yeah. So, zero choose 0, write the 0th row, and we can write the 1 choose 0 and 1 choose 1. So, we can say that this is the 0th row and this is the first row, right. So, and the second row will look like 2 choose 0 and 2 choose 1, 2 choose 2, like this. Of course, we had to put comma if you want to separate them. This will be 3 choose 0, 3 choose 1, 3 choose 2 and 3 choose 3. This is a table. So, this will keep on the length of the row, it will keep on increasing, right. So, note that 0 choose 0 is 1 by definition, and then we do not have a 0 choose 1, because 0 choose 1 will be equal to 0, we do not write it. 0 choose 2 will be equal to 0, on so on. These are all zeros in fact. Here 1 choose 0 and this is 1 choose 1 and 1 choose 2 will be 0. So, 1 choose 2, 1 choose 3, all of them will be this will be 0. So, therefore, there will not be anything beyond this. This on the other hand, this is 1 choose 0 is 1 and 1 choose 1 is also 1. So, we can maybe we can also write the numbers here. 0 choose 0 is 1. So, the rest will be all zeros of case, right. Therefore, we do not write it, and then 1 choose 0 is 1, 1 choose 1 is 1, and then going back here 2 choose 0, 2 choose 1, 2 choose 2. This is 2 choose 0 is 1, 2 choose 2 is 2 and 2 choose 1 is 2 and 2 choose 2 is 1 and the rest are all zeros. Here also there are zeros, here also, because 2 choose 3 onwards it will be zeros. So, we do not write it, all right. So, similarly 3 choose 1, 3 choose 0 is 1, 3 choose 1 is 3, 3 choose 2 is 3 and 3 choose 3 is 1, 3 choose 4 is 0 and 3 choose 5 is 0, like that, right. So, we will not write it. So, this is the Pascal's triangle, this is called Pascal's triangle. Because Pascal had written a treatise on this binomial coefficients, maybe the first one in Europe. So, about binomial coefficients. So, it is known as Pascal's triangle, and of course, binomial coefficients were known in the East before Pascal. So, of course, we can read it in the history of mathematics, all these things. So, then so this is what we were telling, we were talking about the symmetry identity. So, here see there is nothing there is no nothing to talk about symmetry here, 0 choose 0, right. So, but here we have 1 0 choose 1. So, if you take k equal to 0 here and then 1 minus 0 will be 1, right. This and this are equal is what it says, and then here 2 choose 0, put k equal to 0, then that will correspond to 2 choose 2 minus 0, that is 2, then this and this are same in between. So, 2 choose 1 is equal to 2 choose 1, 2 choose 1 is equal to 2 choose 2 minus 1 is 1. Here 3 choose 0 will be equal to 3 choose 3 and 3 choose 1 is equal to 3 choose 2, like that, right. This and this is equal, this and this is equal, like this you pair, right. So, now for instance, this is the n plus 1, this is the n plus 1th row, right, because we started with the 0th row. Sorry, this is the nth row, n plus 1th row, in the sense that we will say we named it as 0th row, the first row. So, this is the nth row of the Pascal's triangle. So, here this will be equal to this will be equal to this, and this will be equal to this, and so on, like that we can pair. So, if n is an odd number, how many entries will be here, because it starts with n choose 0 and n with n choose n, there are total n plus 1 entries, the even number of entries that will pair off properly. If n was the middle one will be n choose n by 2 floor and n choose n by 2 seal. Okay, so both they are equal, right, they will get paired off. N choose n by 2 floor will be equal to n choose n by 2 seal. Not, I am assuming n is an odd number, therefore this floor and seal both are integers, one apart, alright. So, they are going to pair off. While if it was an even number, then what will happen is there are exactly an odd number of things, it will pair. So, the middle one will be n choose n by 2, that will pair with itself, sorry, because n minus n by 2 is actually n by 2, right, n choose n by 2 will pair it with itself, right, while here n choose n by 2 minus 1 will pair to n choose n by 2 plus 1, right. So, like this. So, so we need a proof of this, and it is very elementary. So, this is what we want to show, n choose k equal to n choose n minus k, right. So, we can say that the number of ways, because this is the number of ways of selecting a k subset, k element subsets from n element universe, right. Number of ways to select k element subsets from n element universe. So, but the point is, for each such selection, suppose this is an n element set, this is an n element set, this is n element set, we selected a k element set from here. So, what is the remaining thing? The remaining thing, the number of remaining things is actually n minus k. So, when you select k things from an n set, so n minus k things will remain. So, when you take k things, we have left n minus k things back. So, it is as good as saying that I have selected the remaining n minus k things. It is like I removed these k things and picked up the remaining thing, right. So, you select as you select k things, you are actually selecting the remaining n minus k things also in some way. You can imagine it that way, because this process of selecting k things is equivalent to process of selecting the remaining n minus k things. So, therefore, the number of ways of selecting k things will be equal to the number of ways of selecting n minus k things, that is all, right. So, so if you want an example, for instance, put n equal to say 1 to up to 10, right, that is 10. Now, suppose put k equal to 2. So, you can select say a 2 element set 1 2 from this, but then you have, it is like equivalently you have selected the remaining this set. So, this is the remaining set 6, 7, 8, 9, 10. This is an 8 element set, right. Similarly, you can take any 2 element set, say 5, 6 here. So, then it is equivalent to saying that you have selected say 1, 2, 3, 4, 5, 6 gone. So, 7, 8, 9, 10, right. The remaining 8 things you have selected, right. This. So, the number of ways of selecting these 2 sets here is equivalent, so is equal to the number of ways of selecting these 8 sets, that is what it says. Therefore, n choose k is going to be equal to n choose n minus k. So, if you want to see it in the northeastern lattice, so it's we have seen that this n choose k, what was n choose k? N choose k was like we want to reach from 0 0 to k, say this lattice point, this point was n minus k, right, this point k comma n minus k, this is where we wanted to reach, right. So, I can draw this lattice point, right. So, we wanted to reach from here to here, because total k plus n minus k equal to n steps will be required to reach from 0 to 0 to this point. And of course, it is like out of these n steps, how many steps will be eastern, how many ways you can select the eastern steps, eastward steps, right, east steps, eastward step, right, that is what we were thinking, or mean the steps towards the right, right. So, that will be definitely n choose k, right, that we have already seen this argument. Now, when you want to argue this in a different way, one way to think is, right, you could have argued that this is also to the number of ways to reach here can also be counted by asking how many ways you can select the northward steps, because once you select the northward steps, automatically the eastward steps will get filled. For instance, see here our argument earlier was that we select the second, for instance, first step, second step, third step as eastward, right, and the first k steps are eastward, automatically the remaining n minus k steps will be northward. So, we do not have to worry about the northward steps at all, you just have to specify the eastward steps, right, the steps towards the right, that is only we have. So, that we can take out of the n steps in k ways is what we told. We could have argued the other way also, we could have selected the steps towards the north, that has to be n minus k, right. So, we can select n minus k steps and choose n minus k ways towards the north, and the eastward steps will automatically be fixed. If you want it to be slightly different, so let us say we can also think like this. So, let us say now, right. So, this is a main diagonal, okay, I have drawn it properly, but you can say we can take a point, this is k n minus k, we could have also taken another point which is n minus k k. So, for instance, here it is approximately, right, let us say n minus k. So, n minus k comes here and then the k comes here, something like this, right, suppose k comes here, right. So, it is in some sense like it is the number of ways to reach here, right, that paths, if you reflect about the main diagonal, that will be a way to reach here, right, here. So, this we have to draw better, then it will be clearer. So, the point is maybe you can draw it and it is not worth redrawing the figure and wasting time. So, the point is you can say that to reach k n minus k, the number of paths is n choose k, right, but to reach n minus k k, it should be the same number of paths because of the symmetry, and this will be n choose n minus k, right, even the formula can be written, right, that is what it says. Anyway, so that I leave it to you to figure out, and now the next identity we will consider. This is 2 raised to n equal to k equal to 0 to n choose k. Um, so again going back to the Pascal thing, so this is what we want to prove. So right, so n choose 0 plus n choose 1 plus, if you add these things up to n choose n, what we will get is 2 to the power n is what it says. Note that, so this is starting from here, n choose n is the biggest non-zero number which we can make, because for instance n choose n plus 1 onwards will be zeros, right. So we do not have to convert. So if you consider all these things, it will become 2 raised to n. In other words, from the Pascal's triangle, if you want to see this, yeah, here it says if you add up these numbers, say in a row, in a certain row, this will add up to, here it will be 2 raised to 3, right. So if you want to see the next page, so you want 2 raised to 0, this is the 0th row, right. So here 1 plus 1 2, 2 raised to 1, so this is the first row. 2 plus 1 plus 1 4, it is 2 to the power 2, second row, right. 3 plus 3 6 plus 2 8, that is 2 to the power 3, third row sums up to that. Similarly, nth row if you sum up, nth row will sum up to 2 raised to n if you add up like this. That is what the statement says. Of course, this is not new to us, we have already seen the proof of this using the fact that actually n choose k is the number of k element subsets, and this is counting the total. For instance, what is it counting? N choose 0 correspond to the number of empty sets, that is only one of case. N choose 1 correspond to the number of singleton sets, right. N choose 2 correspond to the number of 2 element sets, right. So 2 element sets. N choose 3 corresponds to the number of 3 element set, and finally n choose n correspond to the number of n element sets itself. If you add these things up, we are actually counting the number of subsets of n, right. And earlier we had shown that by that string, binary string argument, I mean we set up a bijection between the number of subsets of a n element set and the n string, n length binary string, and told that this is actually 2 raised to n, right. Here we are claiming that is indeed. So we, another proof we had shown for this thing is by noting that 1 plus x raised to n is equal to 1 plus n choose 1 x plus n choose 2 x square. This was the binomial theorem, n choose n x raised to n choose n x raised to n, and we put x equal to 1, and then this side became 2 raised to n, right, and this, because x became 1 here, right, all these things will become 1. So therefore this is n, this is n choose 0, sorry, n choose 0 plus n choose 1 plus n choose 2 plus n choose 10. These two proofs we have already seen, right, but in the context, so we can also remember this identity, saying that the Pascals, if you take the Pascal's triangle and add up the elements, the numbers in the same row, right, if you sum up the rows, it will always be 2 to the power something, 2 to the power that row number, that is what it says. Okay, so next one. So of course you can try to get an interpretation of this using our lattice path arguments also. So for instance, you can interpret it like this. So what will be n choose 0, right. So that is, so we are considering the number of ways to reach 0 and n minus 0, right. So 0 n minus 0 would be this point, right, this one 0 n, right, 0 n minus 0 is this thing. And then what is n choose 1? N choose 1 will be the number of lattice paths, I mean northeastern paths to reach from 0 0 to 1 to n minus 1. That means, say this is n minus 1, yeah, this being n minus 1, so somewhere here, right. So this is 1 n minus 1, right. So right now the next one will be n choose 2, that will correspond to the number of lattice paths to reach from 0 0 to this 2 n minus 2, right, and so on, right. And we are actually summing up the number of paths to reach here, here, any of these things, right. So, or finally n choose n. So, this you can see the interpretation in terms of paths. So, that is just to visualize, and then what. The next question, next identity we want to consider is n choose k plus n choose k plus 1 is equal to n plus 1 choose k plus 1. So, this is so an important identity, it is called the addition formula. The addition formula. See, this is for instance in the Pascals triangle. So, what it says is here see, this is nth row, suppose this is nth row, this is n plus 1th row, right. So, let us say n k is equal to this one, say k is equal to 2, put k equal to, sorry, this is 0th row, this is 1st row, k equal to 1, right. So, n choose 1 here, this number, n choose 2 will be here, right. So, now we say that suppose I add this one, n choose 1 and n choose 2, then what do we get? We will get n plus 1, that means in this row choose k plus 1, namely just below this thing, k plus 1, right. So, this and this if you add, you will get this is what it says, right. So, maybe you can in the Pascals triangle, yeah, here in the Pascals triangle, suppose, so I will draw like this, suppose here this is the nth row, say we consider the kth column here, in the kth column we will see n choose k, right, and this k plus 1th column we will see n choose k plus 1. Now, this addition formula says to add these two things here, this and this, and then what it says, it declares that the answer is going to be in the next row, that means n plus 1th row. So, this is the n plus 1th row, and in which column? K plus 1th column, means this column just below this thing, n plus 1 k plus 1, right. If you add these two things together, you can get this thing, that is what it says. For instance, that will help us to create the Pascals triangle very easily. For instance, you can write here, this was your 0 choose 0, okay, and then here the next one also we need, that means 1 choose 0 is 1, and 1 choose 1 equal to 1, so right. And then the third one onwards we can use this formula. We always start with 1 because always any n, for any n choose 0 is going to be 1. So, this is always like this, right. And the second this is the first row onward, first column onwards we can create like this. See, this 1 plus 1 will be 2 here, this and this. If you to get this thing, what you should do is you go to the previous row and take just above thing, this one and this one, and add them together, and then we can write here 2. And of course, this is what should be this. This is always, the last one is always 1, we do not have to worry about it, because that is n choose n, right. For any n it is always 1, right. So, now next number, so here 1. So, what we do is we take this and add them together and then write it here 3. And then to get this number, what do we do? We just take this number and this number, 2 plus 1 is equal to 3, and here it is 1 because and to get this number we add this and this together, that is 1 plus 3 is equal to 4. To get this number we add 3 and 3, this one and this one, right, that is 6. To get this number we add this and this, that is 4, 3 plus 1 4, and here it's 1, right. The next one 4, 1 plus 4, this one and this one is added, we will get 5 here, and now this one and this one is added, 4 plus 6 10 we will get, and then 4 6 plus 4 10, 4 plus 1 5 and 1. What are we are just applying that formula n choose to get the n plus 1th row, to get the n plus 1th rows k plus 1th entry. We are just taking the just previous row, that means nth row, and k plus 1th entry and just previous one, and n choose kth entry, right. Just to get this one we took this one and this one, right. That is what this is, just above this and this previous one that is being added. Like that we can create the Pascal's triangle. So, this is the basic recurrence relation for the binomial coefficients. Once you know the initial values, namely this way how you start these ones and something these ones, and say this one, this we are not creating using this formula, and then yeah, this and this we already wrote. Beyond that we can just produce the entire table using this thing, right. So, we can write down all the formulas, it is very easy that way. So, you do not have to use the explicit formula for n choose k to calculate, see, n factorial by k factorial into n minus k factorial. So, not that this is of course here we have to, for instance, if n is too big we have to generate all these numbers, while of course here we have to do the multiplication, but as such for small numbers this may be easy to write down also, at least we can generate them easily. So, for you, if you know the previous ones, we can easily generate these numbers. This is the way the Pascal's triangles can be generated using that addition formula. Okay, now coming back to the addition formula, namely n choose k plus n choose k plus 1 is equal to n plus 1 choose k plus 1. Here n and k both are non-negative numbers, and then k is smaller than n, and how do we prove this thing? So, we just see the interpretation of both of these things. So, what is this? This is like selecting from n plus 1 element universe, we want to select k plus 1 subsets. The best thing to do is to remove the largest case, say n plus 1 itself, and keep that apart, right. Now, there are two different ways of selecting k plus 1 element sets. So, from the remaining n elements, that means this universe n, so we can select k plus 1 things, all the k plus 1 things can be selected that way. That means, with never putting this n plus 1th element in it, that can be done in n choose k plus 1 ways, right. This is with this term, right. And another way of doing is add this n plus 1, I mean first add him, and then we still have n elements left. Out of that we can select the k things, that is n choose k ways, right. So, this collection always contains this n plus 1th guy and element, right, n plus 1th element, and we are saying that we have grouped the possible subsets k plus 1 element subsets of n plus 1 into two groups. Those subsets which contain n plus 1 and those subsets which does not contain n plus 1. The number of subsets which does not contain n plus 1 is essentially the number of k plus 1 element subsets of n, right, because n plus 1 is removed, right, there is we are not going to take, that is this n choose k plus 1. The number of subsets which contain n plus 1, because n plus 1 is already there, now we only have to have k element subsets from the remaining n, that is n choose k ways, right. So, these two things if you add, we will get this thing, this is what, this is simple. And if you want to, as usual, if you want to look at the northeastern lattice and see what it says, for instance, you know what is this n plus 1 choose k plus 1. So, say some k plus 1 is here, right. So, this is k plus 1, this is the point we want to reach, n plus 1 minus k plus 1, right, that is k plus 1 comma n minus k, this is the point, right, we want to reach from 0 0, right, by northeastern paths. So, of course, so we have k, we have to take k plus 1 eastward steps and the remaining n minus k northward steps, right. This is the number of ways to reach here that way. But to reach here, from the picture we can see that there are only two ways to reach there. Either you reach here and then move to here, or you reach here and then move to here, right. So, therefore, to get the total number of ways to reach here, we can count the number of ways to reach here and add it to the number of ways to reach here, right. So, the number of ways to reach here is easily calculated by, if you know the what is this point. This point is because this was n minus k, right, and this was right, this will be, this point will be, because this is n minus k, this will be n minus k minus 1 comma k plus 1, sorry, n minus k minus 1 comma k plus 1, right. So, the number of ways to reach this point is, we add these things together. So, that will be n choose, sorry, I wrote it wrongly, this point is k plus 1 comma n minus k minus 1, right. So, the number of ways to reach is, so this is, we just add total number of steps is this plus this, that is n, choose the total number of eastward steps here, that is k plus 1, right. This is the total number of ways to reach from here to here, right, and choose k. And to reach here, we need to know the point here, this is n minus k, sorry, k. This point is k, because this is k plus 1 through, so this is k plus 1, so this is k comma n minus k, right. So, to reach here, this is, we add them together. So, the total number of steps is n, out of that k steps is to be selected in the eastward direction, that is n choose k here. To reach here, we have n choose k ways, to reach here we have n choose k plus 1 ways, right. To reach here we have n choose k ways, to reach here we have n choose k plus 1 ways. So, we add the number of ways to reach here, we add to the number of ways to reach here, and then we get the number of ways to reach to this point, right, because to reach here we have either this way or this way, and if we have already reached here, then there is no way of reaching here. If you have already reached here, then we have no way of reaching here, because these are disjoint sets. That's just that addition principle we are using, because we have cut this into two disjoint sets. So, this is only a combinatorial interpretation of what another interpretation of what we have explained earlier. So, that selecting, so putting them into two categories and counting two different what we want to count is the cardinality of a particular set. We are just splitting that set into two disjoint sets and then separately counting the things and adding them together, right. That's all. And that was about the addition formula. And next one is, okay, we have already described what Pascal's triangle is, and now for fun's sake, let us consider a few slightly more complicated identities, which you may try to remember, but these are not as important as the earlier two identity, namely the symmetry identity and the addition formula. So, this, let us look at this one. 2n choose n is equal to k equal to 0 to n and choose k square. How do we prove this thing? It is just for practice. So we are saying that if you sum up from k equal to 0 to n, this n choose k squares, right. We will get 2n choose n. So, do you want to verify it for some small values of n? For instance, n equal to 5, let us see. Will it be too big? I do not know. So we can maybe we can take a little smaller, n equal to 4, let us say. So, this 8 and 2n choose n is 8 choose 4, right. That will be 8 into 7 into 6 into 5 divided by 4 factorial, 2 into 3 into 4, right. So, this will be 70 if I have not made any mistake. So, but this formula, what does it say? 4 choose 0 square, 0 is equal to 1, 4 choose 1 is equal to 4, and 4 choose 2 is equal to 6, and 4 choose 3 equal to 4, and 4 choose 4 equal to 1. So, now square it. So, the square of this 1 square plus 4 square plus 6 square plus 4 square plus 1 square. This is 1 plus 36, sorry, this is 16 plus 36 plus 16 plus 1. So, that is 70, 32 plus 36, 68 plus 2, 70. So, it is the same as what we got earlier, that 70, right. So, of course, this can be useful sometimes. For instance, as okay, at least you have seen that to write it down each of these n choose k terms and square and sum. Of course, if you knew that it is just 2 n choose n, you can in one go you can get the answer, right. So, let us say, well, let us try to prove it. So, suppose this is a combinatorial proof. I mean, that is what we want to, we do not want to manipulate and get, this is kind of combinatorial arguments we are practicing here. So, the first side says this is 2 n choose n, that means from this set 2 n we want to select an n element set. How many ways you can do that, right. The other side says you can do it in the following way. First, group these 2 n things as say 1 to n. So, the first part n plus 1, n plus 2 up to 2 n, the second part. You can think that these are men, these are women, say women, because this 2 n were people, and then there were n men and n women. We just this only asks for just n people to be selected out of this 2 n. We do not care about men and women, but we can do it this way. We can select 0 men first out of this n men, right, and then all because the 0 men we select, that means all n people we select should be women, right. Out of n we select n women, or otherwise we can select 1 man. So, maybe we will complete it tomorrow because the time is over.